second memory in this family called suppressed carrier and double sideband suppressed carrier. So let's look. How can we do it? Okay, so why and how? Why we talk about that efficiency too low. The efficiency is very, very low number. The number for mu is around 5%, so very low. How can we do it? So we have linear modulation with no carrier. That if we do not have carrier anymore, all the information, all the power will be used by power information. So the efficiency now will be 100%. Is 1. So now let's look at more details. Really, what can we do? And the benefit and the price we pay for this new technique. Okay, this is how, right? This is what happened at the transmitter side. So we can find it's even simpler, right, compared with double sideband large carrier. Just message mixed with a sinusoid. Omega C, right, you determine based on which channel you want to operate of your signal, your system. And AC actually is, how much power you want to put for this system. Then we are going to have double sideband suppressed carrier signal. So transmitter side, still very simple. Any problem? Any questions? Now for my transmitter side, information mixed with sinusoid. So this is my time domain signal. This is my free transform. We just use property of modulation, right? Modulation. So we have my original signal still in the signal spectrum. However, we are moved to omega C and also, right, the negative part, minus omega C. Omega C, right, you choose omega C by your application. For example, I want channel 1, right, or I want channel 2, I want channel 100. It's up to me. Okay, so this time when we plot the time domain picture, there is a huge difference. Now I do not have large carrier, right, so this is my time domain original signal. This one is modulated. We can find my envelope similar, right? If my signal is positive. However, when my signal is negative, it's flat, right? It's flat. So my envelope actually is the opposite of your original message. And every time your information pass 0, like here pass 0, we are going to have a 180-degree phase change. We call it phase reversal. So here you can find out this is phase, kind of shifted by pi or 180 degrees. So two things I want to remember. Number one, every time your signal pass 0, there is a phase reversal. Second, my envelope is not the same as my original message. So envelope detector cannot be used for this system. Okay. Any problems? Any questions? Okay. So later when you plot double sideband suppressed carrier signal, make sure you have the phase reversal indicated. Same technique, a little different for my input. So this time my input signal is a digital signal, right? I have 1, 0, 0, 1. If we use double sideband suppressed carrier, we get phase shift key, right? So here, for bit 1, we have this initial phase started from here, right? For bit 0, right? -1, my phase started from here, so we have 180-degree phase shift. We also call DSB-SC. So binary, right? Binary or bipolar PSK. So yeah, pretty much this is better. So this shift key, phase shift key. PPSK we consider the simplest one in digital communication. And if you want to carry more information in this single waveform, you can have more phases, right? For example, here, I start, for example, this is sinusoid start with 0, right? This is sinusoid, sine start from pi. If I have started from here, right? Pi over 2, started 3 pi over 2, I'm going to have 4 different phases. So we can carry 4 different information. There will be two bits, right? 2 bits. And in, okay, this one is not required for digital. Communication. We use Phasor to plot your waveform. So here, I have my amplitude, right? For example, this is A, right? This is minus A. So my phase is 0. Here, my phase is pi. So this one, for example, it can carry positive 1, right? Negative 1. So this is bit 1, bit 0. We call it BPSK. If you have, for example, right, more phasors, right? More phasors. Each star, right, constellation will carry 2 bits. For example, here we have 0, 0, 0, 1, 1, 1, 1, 0. So this is 4 PSK, right? You can have 8 PSK, right? 16 PSK. If you play with your amplitude, the length of your phasor, all this vector will change. So you can have ASK, PSK, but FSK is very difficult to plot by this constellation. So, okay, now we come back. 2 things, right? Phase reversal. Every time you signal past 0, and my envelope no longer the same as my message. So when we do double sideband substrate carrier for digitize the message, we have BPSK for your original information. Oh, I just kind of summarize. My message is negative, give me the same envelope as my message is positive, but carrier flips by pi. We call phase reversal. Phase will be kind of jump, right? Okay, any follow-up questions? So here I could just, repeat previous one. In my frequency domain, we have the spectrum. Move, right? This is in terms of radian per second. This is in terms of hertz. And compared with previous double sideband large carrier, we have the two impulses, right? Two impulses for large carrier. For double sideband suppressed carrier, no impulse, no those two impulses anymore. Just what happened in frequency, right? In frequency. So if this is my original signal's free transform magnitude, right? My phase, so will be moved around omega c and minus omega c. So we can find the spectrum just kind of shifted, right? In frequency. There's no change for your original signal spectrum. We call it linear modulation, right? Just linear transform for your spectrum. But later when we talk about FM, your original signal spectrum will be changed, or will be nonlinear. So next slide, we summarize the transmitter side of double sideband suppressed carrier in block diagram. Time, also frequency is a frequency. So the top one is your transmitter side. Very simple structure. This is my unmodulated, this is modulating signal, my message in time, in frequency. Here is the carrier, right? Cosine omega c time domain. This is frequency domain. And the one thing I want to mention here, later we call your modulated signal spectrum. This portion okay, so the shaded green portion we call the upper sideband, USB, right? Not USB drive, but it's upper sideband. The frequency component is higher than omega c, so we call it upper sideband. The other side, other side we call it lower sideband. Lower sideband. Next, later when we talk about single sideband, we just transmit either the lower sideband or the upper sideband. But here we still transmit both. We can find right now my bandwidth is still twice of original one, so we still call it double sideband. We have block diagram, time, frequency. Okay, phase reversal, okay, phase reversal. Any problems on the question? For this one? Next, I think the next one will be, just remember, we have upper sideband and lower sideband, so we call it double sideband. Okay. Previously, right, for double sideband large carrier, we try to plot the waveform with time. This time, I want you try by yourself first. So, can you please sketch the signal in frequency domain. So I have message, right? I have carrier. Just, so plot. Fourier transform of xt times 3 cosine 2 Okay, can you plot the Fourier transform of ft times eukaryote? Give you 5 minutes, then we take a look together. Okay, so let's work on this one together. Find Fourier transform of the modulated signal. So we know x of t is cosine 2 pi and this one Fourier transform, if you look at your table, right, we get pi so this is 1k, right? Minus 1k x omega pi, right? So I have my original signals Fourier transform plotted over here. After modulation, I should have, right, the original spectrum moved the original one will move around minus omega c and omega c and omega c. So based on this problem, x so my frequency, my Fourier transform of the signal should be half, right, half f omega plus omega c f omega minus omega c, right? Plus omega c minus omega c. This one will move to this is 1 meter, right? 10 to 6.
Isn't it 3 cosine?
3 cosine? Yes, yeah, 3 cosine. So 3 will be here, right? 3 will be here. Okay, I'm going to move this one to here. Let's do this. Let me right over here. Will be Phasor, right? X omega plus omega c. Let me plot over here. So test 10 to 6, right? Minus 10 to 6. So I'm going to move this 2 here and over here. Pi. 3 over 2 pi, 3 over 2 pi. And this is 10 to 6 plus 10 to 3rd, right? 10 to 3rd. This part will be 10 to 6 minus 10 to 3rd. So I have 2 impulses over here and another 2 impulses over there. Move here. Also move just plot, right? Just plot. From original one, moved to your targeted bandwidth, double sideband substitute carrier. So this is one solution based on property of modulation, AM modulation. You can, since we have sinusoid, right? You can also have cosine times cosine, right? You have half cosine alpha. Let me write solution number 2. Signal will be 3 cosine 2 pi. So here, right, you are going to have cosine 2 pi into 3 cosine 6 t. You can also do this way, and for those two different sinusoid signals, from Fourier transform, I have 2 impulses for this one, and another 2 impulses for this one. The final answer will be the same. So we have 4 impulses, right? Here and over there. So sinusoid you can always do that. But if my signal is a general signal, you can use the property of amplitude modulation. Okay. Any problems, question for this exercise problem?
So with double sideband suppressed carrier, we're multiplying the signal by the carrier wave?
Yes.
Okay.
Yeah.
All right.
Yeah. That's right. So when you do that, signal multiply with your carrier wave. Yeah, this is what happens at double sideband suppressed carrier. And this is modulated signal, right? Modulated signal in time. So if I can write down my signal in this format, right? Yeah. 2 cosine multiplication, we have cosine, right? One angle plus another one angle minus another one. So I have 2 phasors, right? 2 phasors. This is omega c plus omega m. This is omega c minus omega m. So this is my modulated double sideband suppressed carrier signal in phasor. Combine them together. Right, this is the real signal. So just based on definition of phasor, we can get this one. Any problem, questions? So I have 2 things to mention at the transmitter side. Then we move to how can we demodulate my signal. Okay, we talk about this one now. So double sideband suppressed carrier signal has upper sideband and lower sideband. The last one. This is the motivation, right? This is motivation. Now my signal's total power, mean square value or expectation of the square of your signal is a square over 2, right? This half from cosine omega c of t. And this is the power of my message, right? My message. So ft square expectation, expected value, or mean square value, the same. They all mean power of your message. So now, total power used for message, for information, for signal, my efficiency is 100%. So this is we achieve that our goal. We want to improve the efficiency. Now we get it 100%. So this is a huge improvement, right, compared with double sideband large carrier. However, right, this is pros. Cons will be your receiver side will be way more complicated compared with double sideband large carrier. So I'm going to just start talk about that one a little bit, and we use complicated mathematics stuff for our sources lecture. So demodulation, as we mentioned before, as we mentioned before, the envelope no longer the same as your original message. So envelope detector cannot be used. Here, so the demodulator we use for double sideband suppressed carrier will be is called coherent demodulation, also called synchronized demodulation. This one not only be used here for double sideband suppressed carrier, also be used later in single sideband and the last one DSB rescale sideband. So in order to implement this demodulation, we need much more compared with just a diode, a capacitor, and a resistor. So we talk about this. Just talk about the. So let's talk about that one. Okay, so we know, right? This one carry all my information. This one also carry all my information. So how can I change this one back to the original one? We shift it again. If we shift back to omega C, we can recover it, right? So this is actually the fundamental, what we do to do the demodulation. This is what we did. So the received signal will mix with cosine omega CT again. If this is the original one, and this is double sideband suppressed carrier. Now I type this signal again with omega C. So 2 omega C, right? Minus 2 omega C. Let me use different colors. So this one will move to overhead, right? And any problem for this one? So this part, type omega C, I'm going to go higher omega C, right? Lower omega. So original omega C now will be 2 omega C and 0, and go back to 0. The other side. The other side, it will go to -2 omega c and go back and go back. So those two, the blue one and the red one will be add together. Can I use this one? Okay, so this is the after fourth step mix with cosine omega ct, and the black one exactly the one we want to obtain, right? So this one will be this one is a modified version, right? Just amplified version of f omega. So how can I get this one? We remove the high frequency parts by using low pass filter. So in your structure of the demodulator, we are going to mix with cosine omega c, then go through a low pass filter. So this is what happens at your demodulator. And we are going to discuss some more details. How can we design our low pass filter? How can we get our perfect reference like a signal to mix with your received signal? Okay, so we are going to talk about more details on sources class. Okay, any other?
So is the one in the middle double or just?
Double.
It's double.
Yeah, double. So if I don't consider any AC for the signal right here, I have I have 12, right? This one will be 1/4, right? Also 1/4. And 1/4 plus 1/4, here I should half. I should half. So this one is double of the red one and the blue one. But compared with the original one, if there's no any AC, right, will be half of your original spectrum. Okay, we have around 5 minutes. Any problems, any questions?